Hi, welcome to Lecture 12, Preparation of a Mono-Bactam core. So here we show 1, which is a compound of interest because it shows antibacterial activity. It's composed of 3 major components: the left synthon 2, which is prepared in the literature; the right synthon 3, which we developed a route to. This is an iron chelating siderophore. Basically, gram-negative bacteria metabolize iron, and the chelates to the iron and pulls the rest of the molecule in with a Trojan horse approach. In black is the core, or the Mono-Bactam. This exhibits the most antibacterial activity of the molecule, and we will go into more details about these type of molecules in future lectures, but this lecture basically focuses on the synthesis of the core. This work was done both by colleagues that I worked with at Pfizer and our CROs over in Europe. Several ideas were generated, including access to the core using a novel 2+2 cycloaddition and using Gardner's aldehyde as a building block, but most promising idea came from the use of ester 5. This methodology was developed by Miller in 1983. Conversion of the ethyl ester 6 to an amine was expected to lead us to the mono-Bach protected core 8. We tried to repeat Miller's chemistry to intermediate 6 and attempted the reduction of the ester using sodium borohydride. Unfortunately, and not surprisingly, complete destruction of the lactam ring was observed. There were many attempts to modify this reaction, but no success was achieved. Basically, you have a activated 4-membered ring, and the hydride would open it up, and you would form hydrolysis product, or destruction of the, with water, you'd form the hydrolysis product. The hydride would also open up the beta-lactam ring, acting as a nucleophile. Taking a step back, we wondered if it might be easier to carry out the reduction on the open chain form. This would increase the overall yield and the number of steps, but avoid the difficult reduction step with the lactam installed in the molecule. Excitingly, we found that the open chain ester 10 was cleanly converted to the diol 11. The deprotection of 13 with TBAF at room temperature was found to give the 5-membered lactone. However, this could be prevented by carrying the reaction out at -40 degrees. The remaining chemistry proceeded as expected. So, utilizing 15, we initially attempted the removal of the Bach group, but discovered the yields for the subsequent deprotection of 17 were not sufficient to complete the synthesis. Reduction of the azide and removal of the benzyl group under neutral conditions was found to give the 5-membered lactam. However, this could be avoided by trapping 18 in situ with 1 equivalent of PTSA. Reaction of 19:1 was found to give various degradation products, but careful control of the reaction time 1 could be isolated in moderate yield.